All right, let's go ahead and start. I can probably use all 50 minutes of this presentation here. So I'm going to just move this over here this way. Okay, so hi everyone. My name is Shashank Chivan. I work at Oracle. I run the in-memory database technologies group where we build the database in-memory product. Today's talk is top 5 innovations of Oracle's database in-memory product. What I'm going to do is kind of give you a little bit of a motivation behind in-memory databases, describe to you Oracle's implementation of our in-memory column store, go into the architecture a little bit, and then kind of break that down into sort of the top 5 innovations that we've developed since the initial release back in 2014. Okay, if you have any questions, it's a very small group, so if you have any questions, just feel free to interject it at any point in time. The safe harbor statement. So we start off with this motivation slide that just basically talks about who really needs in-memory processing today, who's looking for in-memory databases. And really what we're targeting is these real-time enterprises, right? The real-time enterprises need in-memory innovations now. And so what are real-time enterprises? So real-time enterprises are basically enterprises that require real-time analytics. They need to be able to process data at the speed of thought, right? And so there's a whole bunch of examples here with insurance companies, retailers, financial services. All these companies basically need to be data-driven, right? They want to react quickly to data, be agile, move very fast, and also be efficient at this. So those are kind of, they're bringing the requirements in, right? Now, where else are we seeing some requirements and where the trends are coming? So if you look at hardware trends, this is like maybe in the last 4 or 5 years at least, larger, cheaper memory, right? You've got DRAM, you have persistent memory for those of you who were in the talk before this where we talked about persistent memory from Intel. Larger CPU caches, so you got about 32 megabytes of shared L3 cache and Intel's Cascade processors. Larger multi-core processors, 24 cores. Larger SIMD vector processing units. Just really quickly, show of hands, how many of you are familiar with SIMD, single instruction multiple data? Okay, great, a few of you are, great. Faster networks, now we're talking about 100 gigabits per second with Rocky versus 40 gigabits per second with InfiniBand. NUMA architectures and persistent memory. And again, with persistent memory, just to kind of recap what the gentleman said in the last presentation, we're talking about high availability, talking about larger capacity, and we're talking about speed. So that's kind of a game changer for us. All of these hardware trends, along with the requirements coming from enterprise companies, are kind of driving the need for in-memory now. Now is a time when people can actually utilize in-memory and actually can run fast and serve its purpose. So where does in-memory fit across these different tiers? So you have the application tier where you really care about the fastest response time possible, right? So you embed a database directly into the application, and then you get immediate response time. So, and that's where one of our products at Oracle called Times 10 fits in very nicely. The database tier is where we developed our database in-memory feature, which is what I'll talk about for the majority of this presentation. And there we're looking at processing billions of rows per second, right? That's the billions, tens of billions of rows per second. And also dealing with faster mixed workloads. So we want to deal with analytics as well as mixed workloads. And then we'll talk about also in the storage tier. So in-memory can sit in the storage tier. And for us, at Oracle, we build these systems called Exadata systems, which are basically these database machines that we build with best-of-breed hardware. And there we have in-memory data columnar data formats that reside directly in our flash memory. And then we run our algorithms leveraging things like SIMD and so on to make analytics run faster. So I'll talk about all of this in subsequent slides. Okay, so I want to just begin. There's about 5 or 6 some slides. It gives you a little bit of background on Oracle database and memory. And then from there, I'll branch off into what are our top 5 innovations. So again, just a brief background. I don't know how many people are familiar with databases and row versus column, so I kind of like to start off with this slide. Row databases are traditionally used for making transactions run faster. Okay, so if you're looking for a specific row, you want to modify a specific row or some small set of rows, that's where row-based storage, data stores can really perform well. If you care about analytics and you are looking at just a few columns, but really all of the rows across those few columns rather, that's when a column store makes sense. So in a column store, you're only going to touch the columns that you care about. And the data is organized in columns, so they're contiguous with each other. So you can utilize a lot of cool vector processing techniques, which I'll talk about subsequently. So historically, you kind of have to choose between the two, either a row database or a columnar database. And with Oracle Database in Memory, we kind of allow you to have both. And that's where we have our dual format architecture. So some of you may have seen this slide before, this picture before in a couple of presentations. So I'm just going to repeat it again here. So our architecture is kind of unique. Okay, we basically say, I don't know, maybe you want to run analytics, maybe you're going to want to run OLTP. Maybe it's a mixed workload, you're going to have a little bit of both. And so for that reason, we don't want to choose between one or the other. We want you to be able to have both. And so if you see on your left side here, the buffer cache is in row format, and we continue to have the row storage. That doesn't change. Everything that we've had for the last 30, 40 years continues to exist. But in addition to that, we maintain a column store, and that column store is stored in memory. And by maintaining both of these stores and keeping them simultaneously active and consistent with each other, we can get the best of both worlds, right? So the optimizer chooses at runtime, based on the query that it sees, which path to go. Should it go down the buffer cache because it can leverage an OLTP index and just get to these few rows very quickly? Or should it go to the column store and run an aggregation or a join or something analytic heavy that can leverage the data in memory? Okay, this is built seamlessly into the Oracle database. So all the 30 to 40 plus years of technology that Oracle has developed all work transparently with Oracle database in memory. No real changes that are needed whatsoever. Okay, that's the architecture. Going a little bit deeper here just to talk about how data is stored. So again, we're talking about a pure in-memory columnar format. You see on the bottom there that sales table. That still sits on disk like it normally does, always resides there on a persistent store. But what we will do is if you say, bring this table into in-memory, alter table sales in memory, we will immediately populate it into a columnar representation and store them into memory into basically chunks of 1,000,000 rows, which I'll talk about in the next slide. And now both of these, again, are transactionally consistent with each other. There's no changes to the disk format. It's available on all platforms. You can enable in-memory at a variety of different levels. At the table space level, at table, partition, subpartition. You can even say, I only want this column to be in memory. Okay? The only thing that you have to do, there are two things, okay, by default. One is you have to specify how much space do you want to carve out from your SGA to reserve for your column store. That's this parameter, that's this parameter in-memory size at the bottom there. And then the second thing is you have to specify which tables you want to be in memory. That's it. Okay? Going a little bit deeper, I like this slide because it speaks to how we support DML. This slide shows you what we call this in-memory compression unit, or IMCU, in-memory compression unit. What that is it represents a chunk of rows, normally around 500,000 to 1,000,000 rows. And that's we have all the columns in that IMCU for those 1,000,000 rows. Okay? And you see this very special column there called the row ID column. The row ID column is what maps that row back to its storage on disk in its persistent store. And on the bottom, you'll see the extents, extent number 13, extent number 14, extent number 15. That is where the data, the rows, actually reside on disk. And we have this very tight mapping from the rows on disk to where they're located in the in-memory column store. And why this is important, which I'll talk about in a subsequent slide, is it allows us to very quickly map any changes that happen to disk back to its representation in the column store. Okay? It's a very quick mapping, and I'll go into details about that. The other thing about this slide it talks about on that second part on the bottom is you can specify different compression levels, right? We give you the complete control. Oh, you know what? I think you need to turn off use timings, the timings. If you can do that, I'd appreciate it. But while he's doing that, I don't know if you can or not, but you can specify different memory compressed levels. So if you care about performance, then you're going to say compress this for query. That means give me lightweight compression, but I have a lot of memory, so I just want to be able to compress it lightly, but run really fast. And then you can say, you know, I don't have that much memory. I have a large working set, and so you can compress that for capacity. Okay. Can I go into the next slide? Excellent, thank you. Okay, now once it's brought into memory, I'll have one slide that talks about how do we make processing faster. And this goes to the SIMD discussion I just had a second ago. SIMD stands for single instruction multiple data. Single instruction, multiple data. And most modern processors today have the SIMD instructions built in. Intel for sure has it. They have an instruction set called AVX512, which are very large, fat 512-bit SIMD registers. And what this instruction set and registers allow you to do is it allows you to parallelize operations against data elements within that register. So as an example, you see here, find sales in state of California. So I have this table which has a column called state. And the state could be represented as a byte, okay? Even less than a byte really, but each state could be represented as a byte in that column store. And what you need to do is you first load 512 bits of states into this vector register, right? That's 64 states in one load brought into that SIMD register. The next operation is the comparison. It does a vector compare of all of those states, all 64 states, to California, and it does that in one cycle. Okay, so one load, one comparison, and when you're done, you have 64 results, 64 bits that says true or false. And in this way, we're able to process, we're able to scan at billions of rows per second. Okay? Okay. Last slide, I think, on this is that just like scans, we can make all aspects of analytic workloads faster. So joins can be faster because we look at joins and we convert joins using Bloom filters, and we speed up Bloom filters using vector processing. Reporting, if you're doing aggregation and group by, same thing. And I have, again, some slides on that. Okay, these are just some customers. I can skip this slide here for this talk. All right, so I want to get into the top 5 Oracle database and memory innovations. Some of this I kind of touched upon already, like the SIMD vector processing, but let's get into these top 5 category here. So the first thing here is this dual format architecture. A lot of these innovations came out from the very beginning when we first released the product. So when we first released the product back in 2014, dual format architecture, support for vector processing, all of these are what I call our foundational set of features. And to us, they're extremely innovating, and let's go into that. But the main thing here at the bottom, you see fast mixed workloads, faster analytics. Excuse me. So to recap, there's that dual format architecture again. We maintain both the row store and the column store, and that really enables fast mixed workloads and faster analytics. Now I'm going to show you how. How do we do this? Okay. So if you look on the right in the picture, we can have fast in-memory DML because an invalid rows are logically removed from the column store. So what that means is, if you look at that picture, okay, let's suppose that a row was modified. Okay, I got all those X's over there. Now when that row is modified, if you recall, we have a very tight mapping from rows to IMCUs, to where they're located in memory. And so all we need to do is map that back to the column store and set a bit that says this row is invalid. And that's pretty much it. So you can imagine every update you do just requires setting a bit that says invalid, invalid, invalid. Now, how do you get your performance? So if you want to run analytics now, what you need to do is just ignore those invalid rows in that column store and just process the valid rows, right? So if you look at this graph here, you're going to do your vector processing SIMD scan we just talked about, and you're just going to skip those invalid rows. That's that. And for those invalid rows, you're going to go to disk to fetch them. And that's how you are transactionally consistent. Okay? So valid rows, you go through SIMD, and valid rows, you go to disk. Did you have a question? Yes.
So for the column store, do you compress those columns?
Yes.
Then how do you go to the exact row ID for
Yeah, you can compress these columns and still be able to index into them efficiently. So with like if I want row 10, I know how to index into it because the compression I use are using fixed width codes. And even if I didn't have fixed width codes, we have data structures that allow you to very quickly index into it to say this is the 10th row that needs a bit that says it's invalid.
For different columns, it could be in different places.
For different columns, it could be in different places.
The 10th row.
Oh, yeah, I see what you're saying. No, so if you recall, there's this row ID. I've got to go through all this again. I'm just going to skip it. But there is a column in the IMCUs that map to, let's say, row 1, row 2, row 3, row 4, etc. And all we have is a bit vector of how many rows are in that IMCU. Let's suppose there's 100,000 rows in IMCU. So we have a bit vector of 100,000 bits. So if I say the 10th bit, I just set the 10th bit in there, and that's all I need to do. Now, your question is, if I need to retrieve that value, and if it's compressed, you're right. You have to decompress it. Then you get to that row. That's true. Okay? But as far as the DML and saying this is invalid, that's very simple set of bit. Okay? Okay. Okay, sorry for the animation here. Let me keep going. So this is an interesting point at the very last bullet here. Mixed workload performance can suffer if the number of invalid rows accumulates in the IMCUs. If you start getting a lot of dirty rows, then you can see your scan is going to be doing this to basically skip invalid rows, go to valid rows, skip invalid rows. So you need to be able to, what we call, repopulate these IMCUs very quickly, very efficiently. And so that's fast repopulation techniques. Okay, so I'm going to talk about that in this in this slide here. So when that IMCU becomes really dirty, you need to replace it with a fresh copy that has those valid rows. And so we have continuous intelligence, that's what we're calling it, continuous intelligence, to track how dirty an IMCU is. And not just how dirty it is, but how frequently is it scanned. For example, if I have a dirty IMCU with a lot of invalid rows, but it's never scanned, why do I need to repopulate it? Just let it sit there. No one's actually scanning on it. It's okay, right? And then we take a combination of these. We look at our sort of heuristics, and we decide to take action. Do we refresh? Do we repopulate it? Okay, so we have different techniques for repopulating. So the first is called double buffering. And double buffering basically just does this switcheroo. It says, in the background, it will create a new IMCU with refreshed rows, all the valid rows, and once I construct it, I will then switch the old one with the new one. And we keep the old one there during this time because we want scans to continue to be fast, and that's going to be on a column store. If I was to remove it out of a memory, then I have to go to the row store to process those rows. I don't want to do that. Okay? So that's double buffering. The second technique is incremental repopulation. This is just being smart. This is saying, hey, I have dirty rows, but not that many dirty rows, but dirty rows. I need to refresh it. In order to build my new columns, I'm going to leverage what I already have in the old IMCU to build the columns in the new IMCU. So that's just being smart, okay? And the last thing is also being smart. This is saying column level invalidations. This is a very simple example. Imagine you have a query. You have a bunch of queries that are updating two of those columns, those first two columns, but they never really touch the third column. So if I have a query that's scanning just that third column, I should be able to go through the column store and actually scan that third column, even though those rows are invalid. So this is just saying, let the query tell us what we can and can't do. Okay? The last slide here that I want to talk about, I'm just going to skip through the animation here, is how else do we make mixed workloads faster? Well, if you have a mixed workload, if you look on the left side, you're going to have a few OLTP indexes, and you're going to have a bunch of analytic indexes, right, on all the columns that you want to scan on. Well, within memory, you can throw away those analytic indexes and just keep your column store. The column store replaces those analytic indexes. So whenever you need to do an update, you're just updating those OLTP indexes, not the column store. Okay? So that's a combination of how we can make mixed workloads faster. And that is, again, all driven from our dual format architecture. Okay? So that's innovation number one, our dual format architecture. Innovation number two is vectorized analytics. This is basically saying, how do we make analytics so much faster? How do we run at billions of rows per second? And in this picture here, I show you these tables, items and sales. They're being joined with another table called departments, which is being aggregated. And I use this operator called vector. And the idea here is the same technique I told you about with SIMD vector processing. We really want to use that everywhere. And all of as many SQL operations as we possibly can to get at that billions of rows per second. So I'm just going to walk through this slide again, talking about SIMD, so that everybody's on the same page. So for example, if you want to parallelize predicate evaluation, you have a query such as this. Select count star from T where A is greater than 10 and B is less than 20. Okay? So the first thing you're going to do is you're going to load A. And you see how I loaded 4 values of A in one shot. The next thing you're going to do is broadcast a value of 10 across, going to splat 10 across a SIMD register and have it in each of those data elements, so 4 10s. And then you do that vector comparison that does in one cycle 51 greater than 10, 95,182 greater than 10, etc. And it gets you a bit vector that says true or false. And then I do the same thing for B. I load B, I compare 20, I got this bit vector result. I then AND those two together. I then mask them and pack them until I get a simple bit vector. And that's that. And just those set of instructions are able to process for essentially those 2 predicates for 4 different data elements. Okay? So that's SIMD vector processing in a nutshell. These next set of slides, I'm just going to kind of talk briefly about it. The slides have a lot of detail, but if you just hear me out, I think you'll understand what's going on. So we make analytics faster using vector processing on all levels, okay? Joins, aggregations, and so on. For joins, what we're doing here is we're saying, if you, the user, tell us what you want to join against. For example, I want to join against the name column in the vehicles table with the vehicle name in the sales table. If you tell us this, we will store the data the data in those 2 columns using a unique representation that's common to both columns. And that allows us to transform a traditional hash join operator that's quite complicated. You have to hash, you have to build a hash table, you have to probe, you have to gather, you have to do key comparisons. Very expensive join operation. You can throw all that away and just do an array-based index lookup join. You have a code, you look it up into an array. If I find an entry, it's a match. Okay? That's what we can do. And now, that operation I just described to you, here's a bunch of indexes, look it up in this array, do I have a match? That's perfect for SIMD vectorization. And so we first allow this operation to happen, then we use SIMD vectorization techniques to make the joins faster. The second thing here is aggregation. I have 2 sides, the left side and the right side. If you focus your attention on the left side first, this is what we call aggregation pushdown. What we're doing here is when you're dealing with a single table and you have an aggregate or a group by aggregate on it, what we do is we push that aggregation down into the scan nodes. Normally, that's not what happens. Normally, the scan sends all the rows back up to the aggregate row source. And then the aggregate row source adds them up one by one by one by one. And you can imagine there's a lot of traffic. You're sending all these rows back up. But instead, if you push the aggregation down, lots of benefits happen. One is you're operating directly on the compressed format in which the data resides on in storage. Second, you can again utilize these vectorized techniques to aggregate them in one shot. And that's how we make aggregation so much faster with Oracle Database in Memory. Vector transformation is a much more complicated process. I'll just give you the highlights. We're able to vectorize aggregation on top of joins. So the left side was for single table, the right side is for join processing. This is an academic paper that we had written, submitted, was accepted. It's quite detailed. If you're interested in this, you can look at the ICDE paper for vector transformation back in 2018, I believe. Okay, I won't go into more details on that. This is just checking on time really quickly, 24 minutes. I'm going to go ahead and skip this slide here, and I'll just talk about this slide. Oh, question, go ahead.
On the aggregate pushdown?
Yes.
Is that for the row-oriented storage or for the column
This is for Columnar. This is for Columnar. Correct. Huh? Everything that I'm talking about, for the most part, here is for Columnar. Okay. Okay, this is a new feature we announced in our 20C release, okay, back in Oracle Open World a few months back. What we're doing is taking what I just talked about with making joins faster to a whole new level. Okay, and by whole new level, what I mean is we're building a framework that allows you to have SIMD vectorization across every single SQL operator. Not just joins, but aggregations, eventually orders, or sorting, window analytic functions, etc. And basically, we're rewriting our algorithms to be completely SIMD friendly. Okay, the solutions I've talked about before are sort of partial solutions. This is taking it to a very different level. And the picture just shows the concept here. The join operation just becomes a vector processing join. Imagine doing parallel matches all at once. Okay. Okay, so that's it for innovation number 2, which talks about vector processing. Going to number 3 now. Number 3 is basically saying we are bringing in-memory column store performance down to the storage layer, directly into Flash, where data is stored and persisted. Okay. Exadata, but show of hands really quickly, how many of you have heard of Oracle Exadata? Okay, great. So I don't have to go into too many details. So Exadata is, I have one slide here that talks about Exadata's vision, but really just talks about what Exadata is. Exadata is basically a database machine that we build in-house using best-of-breed hardware, as I mentioned before, the best network, the best processors, the best storage, everything so that you, the consumer, can say, I don't want to waste my time building the system. I'm just going to buy it from Oracle. It's tailor-made for Oracle, for Oracle database, for the Oracle RDMS, and that speaks to that second bullet there, that we have very smart system software. So our storage software is smart enough to know how to do predicate evaluation or SQL operations really fast in the storage layer, so that what we send back up to the database nodes or the compute nodes is a filtered set that's already been processed. And so now you have a lot fewer rows that you want to process on. So Exadata is really like our database platform, our go-to database platform. And database in memory is our go-to database analytic workload solution or business analytics solution. And so the two really are married together. They should be married together. And so that's where we put a lot of effort into making in-memory run faster with Exadata. So this slide talks about really at the heart of what we're doing. If you look at that picture on the right, you see the Exadata box. Now normally in memory is on the upper part of that box, stored in DRAM in the database nodes. Okay? That's where you see the in-memory columnar scans. Well, what we also do is down at the bottom in the storage nodes, in where your flash array is, we also store your data in the in-memory columnar data formats there. And why is this important? Well, in the database nodes, you're limited to about 1.5 terabytes of DRAM. Most large real-time enterprises have hundreds of terabytes of data. And that's where Flash comes into place. You can scale your capacity out to hundreds of terabytes. And you get all the benefits that you get with in-memory database with the in-memory column store that you have. There's SIMD vectorization, the in-memory aggregation, the in-memory join processing. All of those goodies that we talked about automatically apply to the processing of the data that's sitting in the flash cache. Okay? And, super important, this is completely automatic. There's no user intervention. Unlike in memory where you have to say alter table, blah, in memory, every table, whether it's OLTP compressed or uncompressed, they're all qualified to be populated in the flash cache automatically using this representation.
Now you have to make it consistent with the rows stored.
It's already, so the data is already stored, and so it's already, again, same technology in terms of how we maintain consistency. There's no change. This is a quick slide that just talks about performance given the amount, actually I have some time here. This is really cool. Before we had database in memory, before we had database memory, we had something called HCC, hybrid columnar compression. Some of you may be familiar with that. HCC blocks are basically disk blocks. They persist in storage, but they store their data in columns. It's kind of a hybrid representation because it's on disk. It uses 64K blocks, and then it stores your data in columns. Now, on Exadata, we would store those blocks in flash. So you kind of got the I/O benefit. You're not going to disk, you got it on flash. That's the biggest benefit. Now, if I compare that to what we have now with database and memory, we call the database and memory columnar data formats cell memory. So if I compare cell memory over the traditional columnar flash cache that we had prior to database and memory, you can see this is a star schema benchmark. Some of you may be familiar with that, very popular benchmark used in academia and industry. You can see 5x faster performance for various queries, 3x faster, 1.5x queries. And these are very complicated analytic queries with joins, aggregations, and scans. But you can get even faster performance if you're doing simple aggregation or group by aggregation, easily 10x over what you already have in the flash cache. Okay, one other really cool thing that we architected on Exadata is allowing you to have better fault tolerance and also better performance. So I'll speak to the fault tolerance part here. Normally, if you're on a cluster, a rack cluster, you have multiple nodes. In this example, 4 different nodes. When you populate your tables in memory, it's going to go to one node, and that's where your column resides, or your IMCs reside. On Exadata, we allow you to duplicate this so it can reside on yet another node. And this is great because now any failure that you have, there's no impact because the query can just be redirected to the other node. And you can go beyond that. You can also duplicate across all nodes if you really care about fault tolerance. And not just fault tolerance, performance, because you can go to any node, and when you access your data, it will all be local. You're never going to go remotely to another instance to retrieve that data. Okay, so that's 3. Number 4. Number 4 is intelligent automation. And I bundled automation in with storage tiering. So automatic in-memory management and storage tiering. So let me talk to you about that. Okay. So with database and memory, when we first released the product, we had something called manual in-memory management. And by manual memory management, what I mean is if your column store becomes full, you don't have enough space to store all of your tables, you already brought enough in, the poor DBA has to decide what should be evicted out to make room for something else. Okay? It's a store. It's not a cache, it's a store. And so the DBA is responsible for managing what goes in, what goes out, okay? And so the desired outcome, as I mentioned in red here, is you want to keep the hot objects in memory and remove the colder objects. And so this is where we said, okay, we need to be smarter. We need to basically have automatic in-memory management. And it's not difficult to do. Oracle already has something called heat map, and heat map tracks the heatness, so to speak, of different tables. How hot is this table? How cold is this table? Meaning, how often am I accessing it? How often am I not? And with automatic memory management, you can eliminate all that trial and error regarding what should be in memory and what shouldn't be. So, you see the brain over there. It observes the access patterns. Okay? It categorizes tables based on what's hot, what's intermediate, what's cool. Right? It does that. Once it classifies, it takes action. Right? It decides what should I populate and what should I remove. Very simple. Okay? And it's simple in concept, difficult obviously in practice because we got to get it right. If we get this wrong and we're running automatically, you're never going to trust our automation again. So we got to get this right. In 20C release, we go even further. We say you don't even need to declare anymore which tables should be in memory. We will automatically assume all tables you touch will be in memory. And then we'll take action. Again, what should be in memory, what shouldn't be in memory. Okay? We do all sorts of cool things. As we keep going and innovating, we're going to leverage more and more or add more and more into this automatic in-memory framework.
Does it also
Yes.
at the partition level where you
Yes. I'm sorry. So when I try to say, I generalize by saying table, but again, tables, partitions, subpartitions, and again, even at the column level. Okay? That's correct. That's correct. The one thing I didn't show is a slide that shows a difference in performance between in-memory versus flash. So there is a significant benefit with having your data in memory versus on flash on Exadata. They're different tiers, right? So yeah, you still want to be smart about what tier data belongs into. I'm going to skip this slide here on hybrid and memory scans. And I'm just going to jump to persistent memory now. This isn't, again, related necessarily to automatic and memory management, but it is something that's come up, and I want to just talk about this briefly. So any of you familiar with Exadata X8M that was just announced at Oracle? Okay, a few people familiar with this. So persistent memory, again, if you were in the talk just before this, persistent memory is a new silicon technology pretty much spearheaded right now by Intel and marketed as Optane, 3D Crosspoint, Optane, I can never say the data center, yeah. 3D Crosspoint is at DC something, data center, persistent memory. And so anyways, with persistent memory, you get kind of three big things here. You get the capacity, about 3 times the capacity of DRAM. You get slower latency, okay, so slower than DRAM, but much faster than flash. And you get persistence, okay? You get persistence. That means, again, your data is stored in persistent memory, you pull the plug, you plug it back in. Theoretically, conceptually, the data should be in PMEM still. Okay, on Exadata X8M, you have persistent memory sitting in the storage nodes. Okay, you have, I think we go up to 1.5 terabytes per node, which is a 2-socket system there. And you see on that right side, I already talked about there on the right side, disk, flash, persistent memory, DRAM, faster as you go up, higher in costs as you go up. Okay, so that's persistent memory. On X8M, the focus there is on OLTP. The idea here is you can do RDMA, or remote directory memory access, that goes directly from your database nodes and talk directly to the PMEM DIMMs. And it says, go fetch me this row, come back. You bypass the kernel, you bypass other networking, you bypass context switches, all that's bypassed. That's where you get the best performance, okay, just reading that data. For analytics, there's a side effect. Okay, so because you're able to bypass everything, those storage CPUs now become free. They're freer, I should say. And because they're freer, you can use those extra CPU cycles to make your analytics run faster. Again, on that flash cache with the in-memory database, in-memory column, the data formatted data that's sitting in the flash cache. Okay, how do we leverage persistent memory for in-memory, for database in memory? So we presented the slides at Oracle Open World with Intel. If you look on the left there, today, you can't always fit your data into memory, as I mentioned, right? Limited to 1.5 terabytes, let's say, of memory. So in that case, your queries are going to go against the column store in DRAM, but also against the row store on disk, because not everything fit. And DRAM DIMMs can go up to 128 gigabytes. No one buys them because I don't think anybody buys them. They're very, very expensive. So that's some categories on what today is. With persistent memory now, okay, you can theoretically fit your entire workload into memory. And with memory mode, now memory mode is a specific mode that you can run with persistent memory where it puts a DRAM DIMM that serves as a cache in front of your persistent memory DIMM. And as a result, it makes the latency of access almost at the speed of DRAM. As long as your hot tables or your hot data is sitting in that DRAM cache, you're basically going against DRAM. And these DIMMs can be quite large, up to 512 gigabytes, okay, versus the 128 gigabytes on DRAM. And so now you take those two things, plus you add an Oracle 20C where we bring in our innovations with in-memory vector processing and join processing, all of that. That's where we showcase this. And so what we did is we ran this, a workload. If you look on the left and the red circle, that's basically what you get today, where not everything fits in memory, okay? This is 18 billion rows of the star schema benchmark. And DRAM is only 384 gigabytes. Okay, I think it held about 70% of the rows in DRAM and 30% on disk. And it took 130 seconds to run. And if you look in the middle, now I'm running in memory mode. Everything fits in memory. And I get 18 billion rows in 12 seconds. And now if you run with Oracle 20C, leveraging the in-memory vector processing, the new deep vectorization framework I talked about, you're running at 3 seconds, okay? All right. Last thing, second to last thing here is converged analytics. We are really trying to position ourselves as a one-stop shop. It's one database that you need to go to, one database for all. Relational, text, JSON, spatial, everything could be done on a single database. There's an earlier talk that Tatanka Lahiri gave, I hope some of you attended that, that talked about why we believe strongly in this. Again, this slide is very detailed. I'm just going to speak very quickly on this. We have a lot of cool technology when it comes to converged analytics or multimodal workloads. So JSON, we store JSON in a very cool binary representation that's scan friendly in the in-memory column store, in a very nice compressed representation. So when you want to run your scans against it, you go against this binary representation and you're blazing fast. Okay, I mean 20 to 60x is what we've shown here. I've seen even higher numbers, depends on the operations that you're trying to do. We also have support for external tables. So if your data is sitting somewhere on a Hadoop or in an external file in the object store, you can bring that into the memory column store. And now you're easily running 100x faster. You're not going over the network, or you're not working with a disk format. You're having everything in memory. We make spatial analytics faster. Okay, so I don't know, any of you care about spatial? Any of you run anything with spatial? Spatial is kind of a hot thing. These polygons take up space, and they take up space in your column store. So we have very cool representations of your spatial object in your column store that summarize what this object represents. And using that summarization, you can process filters significantly faster. And again, I think of our memory column store as kind of an open bucket. You can put whatever you want in it. Any really cool data structure, any cool representation, anything that you want. We have the framework, the dual format architecture that allows us to stay transactionally consistent, so we can do whatever we want, right? And so this is an example. We just represent some summary of the spatial polygon and store that in the column store. Same thing on text. We can store an in-memory text index in the column store. You don't need to have an on-disk representation of your text index. So when you want to run a query that says, find me all the documents that have these words in it, now you're going through a very cool, different data structure, basically a hash index in our case, that's an in-memory friendly data structure that, again, you can use SIMD vectorization to optimize its access. Okay, so that's my summary here. 1, 2, 3, 4, 5. I think I may have skipped. I think I said 4 when it should have been 5, so I apologize. But so, just to summarize really quickly, this has been our roadmap, okay? We continue to innovate since 2014 all the way up to now in 20C. Lots of cool new features there. This is a slide that just talks about, from the analyst perspective, where database and memory fits in the set of other competition that we have. And back in 2017, it put Oracle strongest in both current offering and strategy. But more importantly, just now hot off the press about a month or so ago, Forrester again released a new report here on something called Analytic data platforms. Translytical data platforms basically is mixed workloads. So if you care about analytics and OLTP, again, it ranked Oracle at the top again, both on current offering and strategy. And again, those innovations I talked about, those are the quotes that were given. Dual format database, that gives us mixed workload and analytics. Multi-model, that's the converged analytics I talked about. Do not require any changes, that's the automation that I talked about. Okay, and the storage tiering and all that. Okay, so that's it. This is a slide here. If you want, take a picture of it. Gives you a lot more resources, people to talk to, information on the web that you can access if you want to learn more about in-memory. Any questions? Question?
So for the columnar data store, what is the best practice? How much of your memory should be allocated to the columnar versus your regular database?
So Depends on your application, right? If you're a mixed workload, you may, or you may have some analytics at the beginning of the day and maybe some OLTP at midnight or something like that. It really depends on that in terms of how you size your column store versus how you size your buffer cache. Today, one of the problems is where we're not fully automatic, okay? We don't auto-size this for you. We don't say, hey, I'm going to start off with a 0 bytes for the column store, everything else for the buffer cache. And then I say, I see some analytics, let me grow my column store. And then I say, I see some OLTP, let me shrink my column store. We unfortunately don't do that today. So that's kind of a manual thing that you would have to do. But if you know that your particular workload is always going to be one or the other, let's say it's always analytics, I would go full blast. Take your SGA, maybe 80% of your SGA is the column store. I don't know if we have any collateral online. Andy Rivenes, who's our PM, isn't here. We might have some information online that gives you some more advice on how to size this based on your workload. If I can, I'll talk to you after this and introduce you to our PM. Okay. Question?
So going back to the column store materialization in memory that in Flash.
Yes.
So in memory, I've been lazy materialization, but we don't do enough.
You.
Now that you're persisting it, can that be greedy?
It's not persisted. Good question. So where it's stored in Flash, it's a cache. So it's a Flash cache. It's not persisted in that cache. Okay. So think of the.
So it is on the. Okay. So it is in the.
It's only on storage do we persist it. In the Flash memory, it's a cache.
On SSD, you're keeping it only in the Optane.
No, the Optane DIMMs are totally separate. Optane DIMMs.
So when you cache it over there, when you
Yes.
in memory and you put it, what is that storage?
That's Flash. That's Flash SSD drives that we store. Okay, so.
Then you could actually go ahead and do it ahead of time.
Populate ahead of time? Yeah, okay, that's a good question. So you mean bring it into Flash ahead of time is what you're saying, right?
So you avoid basically this quote-unquote serialization, this
Yeah, that's a good question. Okay, and a good point. So we are actually, it's interesting. There are various different POCs that people have ran, and they say, I didn't see any benefit because it wasn't brought into the Flash cache or in the column store right away. And so and then we say, run it a second time and you'll see it because it needs to get into the Flash cache. So I think to your point is we should bring it in right away. And so we do have a solution for that. We just don't, it's not in the current release as of right now. That's a good point. Any other questions?
Cindy.
Yes.
In my experience, if you turn on Cindy, clock frequency drops by as much as 1 gigahertz because it cannot dissipate power. So you don't get as much speed up as you theoretically could. What was your experience dealing with Cindy?
Similar, it depended on the instructions. So I've seen this with like the gather instruction. We did talk to Intel about this. I think they even put out a note of some sort, I forget what they call it, that's saying that you do see a drop in frequency here. The reality is depending on the operation, if it's a simple scan, you become bandwidth bound no matter what because you're just loading, comparing, and that's it, and you're done. So you're really just saying, I'm waiting for you, DRAM to send me data. When it comes to more complicated operations, presumably you would see a performance penalty there. Honestly, we didn't measure beyond that to see how much of a difference is. We actually almost always ran with the throttling disabled so that you're running, full speed at I forget what it's called, but the max CPU frequency with turbo boost. Yeah.
Turbo is disabled by if you turn on Cindy.
Yeah. Sometimes. Yeah. That was with AVX512. There's certain, as I recall, there's certain instructions where that happened. That's my memory at least. We didn't see a dramatic, to be honest with you, we didn't see a dramatic loss of performance when we were testing with AVX512. Only for certain instructions, like I mentioned with the gather instruction, we've seen that. But it sounds like you've seen a pretty significant loss of performance across the board in various different operations, or just
In whatever
anything. Okay.
Also, I read some blog, I think including Intel, talk about that actually they have to lower down. They can't really run at boost frequency.
Okay.
Because they can't dissipate the power because they have got dual SIMD lane per core. So
Yes. Was that specifically with AVX 512? Did you see this?
512.
Yeah. Okay, that's what I thought. Okay. Yeah. Yeah. So that's as much as I know. We did, like I said, where we saw a benefit with AVX 512. To be honest with you, most of the benefit was enabling us to vectorize the rest of our workloads. The new instructions allowed us. AVX 256 also did this with gather. So gather basically allowed us to say, okay, the rest of my pipeline can be vectorized now. Whereas before it's like, okay, I can only do a load, and now I have to do one by one by one by one. And so that's where we saw speed up. I don't know about the degradation on the frequency side other than the gather. Okay. Any other questions? Awesome, I think it's beer time, so thank you.